Dear all, assalamu alaikum everyone. This is your last lab of EEE 4704, and this lab deals with linear block codes for error correction decoding. If let us have a quick glance at the lab sheet first. So the lab sheet consists of a big theory part followed by a model that is built in the Simulink, that is, you'll be building your linear block code in your Simulink with the help of some encoders and decoders. And the properties of those encoders, decoders, and of those blocks are also given in your lab sheet. So you can build it on your own. And then that is followed by two codes. If you have a quick look at the codes, you'll see that the codes are pretty easy to understand as well. That is, no fancy built-in functions have been used here. If you understand the algorithm properly, you'll be able to understand the code very nicely or very easily as well. So to understand the algorithm, you have to understand the theory part first. Now, let us talk about linear block codes. Linear block codes, okay, let me check first if the recording is happening or not. Okay, recording. The lecture has been recorded. So, what are block codes? Block codes are a class of parity check codes where message bits before being sent on your channel are being coded by adding redundant bits to them, so that after they're received, after the coded message is received, that coded message can be checked for errors and at circumstances can also be corrected. So why are they called block codes? Why this particular type of encoding is called block code? Because a block of message is converted to a block of code word. Okay, so a block of message is coded in a way that is converted in a block of code word. So the message might be of k bits. Okay, and we are adding some redundant bits to it. And by adding some redundant bits to it, we form our code word. So the code word will consist of your message bits and your redundant bits. So let's say that the code word is of n bits. Okay. So this is the basic of block coding. Your message bits or a block of your message is being converted into a block of your code word. That is what linear block coding means. Now, linear block coding, that is what block coding means. Now, why do we call it linear? To understand that, we have to understand all the possible messages and all the possible code words that we can form from the bits that we have. So if we have k bits per message, then how many different messages can we have? That is, if we have 3 bits per message, and if the bits are all binary, then we can have 2 to the power 3, that is 8 messages in total, right? 8 different messages in total, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. Similarly, if we have n bits per code word, then how many possible code words can we have? We can have 2 to the power n possible code words, right? That is, if, for example, if your n is 6, then we will have 2 to the power 6. We can have 64 n-bit blocks, right? But we can have 8 messages, right? Or 2 to the power k messages. So even though we have 64 possibilities of code words, among these 64, 8 of them will only be considered as our code words. We'll be calling the n-bit blocks that are associated with our messages, or that are mapped from our messages, as we can call them as code words. The rest of the n-bit blocks will not be called code words. Only the n-bit blocks in your 2 to the power n blocks, among your 2 to the power n blocks, only the code words or only the n blocks that have been formed or that has been mapped from your messages will be called code words. Okay, so although you can have 64 in you can have 64 blocks of n bits or 6 bits for this case. Among these 64 blocks, only 8 of them will be my code words, or only 8 of them can actually be mapped from my message bits. Okay, so now why would we call it linear? So let us see why we will call it linear. The linear name comes from the fact that let me first erase this. So if we have n bits for each code word, we'll have 2 to the power n possibilities of code words, but among them only 2 to the power k of them will actually form code words. Okay, the rest of them will not be addressed as code words. So let us give some names to these sequences. So let us name our sequences tuples. Okay, from now on we will address our sequences as tuples, and when we address a sequence we'll also mention the number of bits in that sequence. So for example, for message bits or for messages, I can have 2 to the power k possible sequences, right? So I'll say that I can have 2 to the power k tuples of messages. And how many bits will each of these messages contain? K bits, right? So I'll say that I can have 2 to the power k tuples. And for n bits, I can say that I'll have 2 to the power n tuples. Okay, so if I represent it in a vector space, then I can say that I can have 2 to the power n tuples, or 2 to the power n 2 to the power n sequences consisting of n bits. Okay, so among these vectors, among these 2 to the power n vectors, 2 to the power k of them will form my code words. So 2 to the power k n tuples will form my code words only if these 2 to the power k n tuples form a subspace that fulfills 2 criteria. So the first criteria is this subspace must contain an all zero vector. And the second criteria is this subspace should have a closure property. So what is a closure property? A closure property is nothing difficult. It's just the fact that whenever we add two vectors inside my subspace, the resultant of that will also exist in my subspace. That is called closure property. So here, when I'm talking about adding them, I'm actually modulo adding them. Okay, modulo to adding them or XORing them. So if my subspace consisting of 2 to the power k n tuples fulfill these 2 criteria, then I can say that this subspace is a linear block code, or I have successfully done my linear block coding. Okay, so this is what linear block coding means. Now let us move on to the next part. So you have learned what linear block coding is. Now how would my encoder code my k-bit messages into my n-bit code words? How would my encoder do it? My encoder could use a lookup table. Okay, for example, there is a lookup table where there are k-bit messages, and each k-bit messages correspond to n-bit code words. Okay, so this lookup table method is easy or is convenient whenever my k and n are of small values. Okay, that is, if my n is, for example, 6, my k is example 3, then how many code words can I have? I can have 2 to the power 3, that is 8 code words, right? So I'll have 8 columns in my lookup table. But if my n is, for example, 16 and my k is, for example, very high, 10, then I would have 2 to the power 10. I would have to have 2 to the power 10 columns in my lookup table. That would actually take up a lot of space in my encoder, and this will not be convenient for our design. So to avoid that, what we can do is instead of storing all the code words, or instead of storing a whole lookup table, we can store a generator matrix or a matrix from which we can actually get to all of our code words. So instead of saving all the columns, or instead of saving all the possible code words, what we can do is we can store a small matrix that would contain some n-bit code words, that would contain a few n-bit code words, and those code words, when linearly combined with my message, would give me my corresponding code word. Okay, now this matrix, which is known as the generator matrix, because from here we are actually generating all of our code words, this generator matrix is obtained from the subspace that we talked about. This generator matrix is obtained from the vector space of 2 to the power n tuples. Okay, and from that vector space, we can narrow down the vector space to a subspace, which actually consists of 2 to the power k n tuples. So from this subspace, we can find out some vectors, or we can find out some sequences which can actually work as generator matrix. And what should be the criteria for those vectors? Those vectors should be linear. Okay, so those vectors should not have closure property. That is, adding those two vectors should not result in the third vector. Okay, so from this subspace, we can find out k n tuples which are linear to each other, and those k n tuples will form my generator matrix. So I'm naming my generator matrix G, and G will consist of k n tuples. Okay, that means if my k is 3, if my message consists of 3 bits, then I need 3 vector sequences. Okay, so v1, v2, v3 in my generator matrix. After I find out my generator matrix, I will only have to store that in my encoder, so that whenever my encoder encounters a message bit or encounters a message, it will linearly combine that with my generator matrix to get my code word U. Okay, so you see here, you are to find out the code word, you are multiplying your message with your generator matrix. And if your message is, for example, 3 bits, what you are actually doing, and if your message is 3 bits, then your generator matrix will contain 3 vectors, and your ultimate code word will look like this. It will be M1 V1 plus M2 V2 plus M3 V3. Okay, so M1 is basically your first bit, M2 is second bit, M3 is third bit of your message. So the multiplications that we're doing here are modulo 2 multiplications, which are basically your AND functions and operations. And the additions that we're doing here, your modulo 2 additions. These are basically your XOR operations. Okay, so do not confuse it with your conventional addition and multiplications. So you see, this is how coding is done, encoding part is done. Now we will, after this encoding part is done, then this code word is sent across your channel, and then the receiver collects your code word and decodes it to check for errors and to correct errors. So how that is done, before we learn about the decoding part, we have to learn something more about the encoding part. Now, linear block codes also have types. There are some linear block codes which are called systematic linear block codes. Okay. So what are systematic linear block codes? Systematic linear block codes have their code words mapped in such a way that a part of their code word will directly correspond or will directly contain the message bits. Okay, and the rest of them will be the redundant bits or your parity bits. Okay, so that's how a systematic linear block coding works. So whenever we want to have a code word that will consist of message bits in one part and parity bits in the rest of its parts, then we will call that a result of systematic linear block coding. Okay, and to get to such code word, we need to use a special form of generator matrix. Our generator matrix must contain an identity our generator matrix should contain a part that corresponds to that is an identity matrix of dimension k, and the rest of the part should be a parity matrix. Okay, so that is how a generator matrix should look for systematic linear block coding. Why should it look this way? As I have already said, this identity part will help to generate a code word that has message bits, and this parity part will help to generate the parity bits, okay, in your code word. So in systematic linear block coding, your code word will contain message bits either towards the end or towards the front of your code, and the rest of the bits will basically be your parity bits. Okay, so to get your message bits directly as they are, to map your message bits directly as they are from your messages into your code words, you need to use an identity matrix, right? That's why your generator matrix will consist of two parts. It will consist of an identity matrix either here or either in the first part, and the rest of them would be parity matrix, okay? Will contain parity bits. So you see that has been illustrated here. Okay. So this actually makes the checking easier. Whenever decoding will be done, it actually makes the decoding easier because a certain part of your total code word will be your message bits and the rest of the part will be your redundant bits, right? So if your message bits, original message was k bits, so among the n bits, k bits of your code word will be your message bits, and n minus k bits of your code word will be your redundant bits. Okay. Now let us move forward. So that's how your coding is done. Okay. So how is the encoding done? Let us, if we summarize it, we'll see. If I summarize it, then I'll see that the encoding consists of deduction or finding out, extracting a generator matrix G, and then we just have to linearly combine it with our messages to find out our code words. So that is what is done at your encoder. Okay. Now, at what happens at the decoder part. So I am sending from my receiver my code word, okay, U, and I'm sending it through a channel, and then my code word is being received at the receiver. So whenever a data or a content is sent through a channel, there are possibilities of errors being introduced into them, right? So let us call the channel errors E. So the receiver will receive your original code word plus your error, right? So let us name our received code word R. Okay. So the code word that I receive will be R. This is just a modified version of your U or the code word that you had sent. And this modification is introduced by the channel error and some other errors on the way. Now, our job will be, or at the receiver side, our job will be to detect if an error has occurred in your received vector or not, and then it will all try to correct that error. So your decoder basically does two things, or your receiver is responsible for two things. First of all, it is responsible for detecting the error in your received code word, that is R, and the next step will be, the next step that your receiver or decoder should take is to correct the error in your received code word to get back to your original code word, or to deduce the original code. Okay, so the first step would be to detect if an error has occurred in R or not. To do that, we do syndrome testing. Syndrome testing. Okay, so syndrome testing is basically multiplication of your received code word with the transpose of your parity check matrix. Now, what is your parity check matrix? Parity check matrix is denoted by H, and parity check matrix is basically a matrix whose rows are orthogonal to the rows of your generator matrix. Okay, remember you had a generator matrix. So you had a generator matrix here. So parity check matrix H is basically a matrix whose rows will be orthogonal to the rows of your generator matrix. So if that is followed, if that principle is followed, then your parity check matrix should look like this. Okay. Now, if the rows of my parity check matrix are orthogonal to the rows of my generator matrix, then the combination of my generator matrix with the transpose of my parity check matrix should give me what? It should give me a zero vector, right? Or it should give me a zero matrix. Now, if this principle exists, then can you tell me what will be the result of multiplying my code word with the transpose of parity check matrix? My code word is basically what? Message vector into generator matrix into message vector into generator matrix, right? So if I expand my code word into mg, then these two parts will be 0. So m into 0 would actually give me a 0 vector. Okay. So that means if my received vector is equal to my code word or the code word that was sent, then if I multiply my received vector with H, that is if I do syndrome testing, then my R can be replaced with U, and U into transpose of my parity check matrix would give me a 0 vector. So when my syndrome testing gives me a 0 vector, that is, gives me a row of k zeros, okay, or gives me a 0 vector, I can say that my received vector is equal to my code is equal to my sent code word. That is, the code word that was sent to me has been received by my receiver. That is, there was no error in the channel, or no error was introduced into my code word while it was traveling through the channel. Okay, since no error was introduced here, that is why the code word that was sent had been received by my receiver. However, if an error exists, then what will happen to the value of the syndrome? Let us have a look at that. See, if my R was U plus E, okay, U plus E, that is my received code word consists of the original code word and some error. If that was the case, then my syndrome would be, my syndrome is R into parity transpose of my parity check matrix, right? So this R can be expanded to U plus E, HT, right? So UHT plus EHT would give me, this would give me a 0 vector, but this would give me a non-zero vector, right? If E had a certain value. If E was 0, that is, if there was no error. If E was 0, then this syndrome would be 0, right? But if E is not 0, then this syndrome will be a non-zero vector. And whenever my syndrome is a non-zero vector of k bits, I can say that an error is present in my received code word. So the detection part is done through syndrome testing. The next step is to try to correct this error or try to find out the correct code word. So to do that, we will be using the result of the syndrome, okay? So the result of the syndrome will be of k bits. That is, will be the same as the number of bits in your original message. So for example, if my syndrome is if my messages are of 3 bits, then my syndrome will also be of 3 bits. You can do the calculation yourself and you can see why it's 3 bits and why it's not other bits. Okay, so for example, my syndrome is of 3 bits, 0, 1, 0. Okay. Now, from the syndrome, we can actually deduce or we can actually find out what error has occurred in my received code word. So for that, we need to use a lookup table. So you see this lookup table tells you that for which syndromes, which error patterns have occurred. So for syndrome 010, the error pattern that has occurred is this. This means your received code word has an erroneous bit at position 2. Okay. For example, the code word you had sent is 10011. Okay, this is the code word that you had sent, and the code word you received was 111011. So you can clearly see that the error has occurred at position 2, right? So that will be reflected in your error pattern. Okay, so if you did not have your original code word given to you, and if you only had your received code word given to you, then just by looking at the syndrome and comparing it with the error pattern, you could have told that the received vector has an erroneous bit at position 2. So by using this lookup table, you can actually tell which error pattern or corresponds to the error that has, or which error has occurred in your received vector. So if you can deduce the error that has occurred, and if the received vector or the received code word is already known to you, then you can easily find out your original code word, right? Your original code word was U. So original code word would be your received code word minus the error pattern, right? However, in modulo 2 operations, there is no minus. This will also be XOR, okay? So if you can deduce your error pattern, you just have to add it to your received vector or to your received code word to find out your original or your correct code word. Now, if you look at this lookup table, you'll see that this lookup table or this syndrome testing is able to detect all 1-bit errors in your received code word and only 1 2-bit error. That is, if your received code word has 1-bit error in any of the n positions, your receiver or decoder will be able to detect it and will be able to correct it. However, if your received code word has, for example, 3, 4, 5, or 6, or more than two and more than two errors or more than 2 erroneous bits, then your syndrome testing will only be able to detect the error but won't be able to correct it. Okay. And for 2 bits, not all 2-bit errors can be corrected by your receiver. Only the 2-bit error pattern that corresponds to this will be able will actually be your decoder will be able to detect only this error pattern. Your decoder will only be able to correct this error pattern. Okay, so if your error pattern had looked like this, if it was 1 0 0 0 0 1, although it's a 2-bit error pattern, your detector or your decoder won't be able to correct it. It will only be able to correct this 2-bit error pattern. Okay, so what are the limitations of this decoder? This decoder can detect all kinds of errors, but it will only be able to correct all 1-bit errors and this particular 2-bit error. Okay, so that's whatever I have said has been written here. And the next step is error correction. We have learned about error correction. Now, using the principles or the things that I have said, they have built a decoder, okay, using your logic gates. So, for example, this received vector has 6 bits, okay? This received vector has 6 bits. So if you go for syndrome testing, then syndrome testing would look like this, right? R into H T. So R is a 6-bit code word, right? So R1, R2, it will contain 6 bits, R1, R2, R3, R4, R5, R6. And then there will be a parity check matrix whose transpose you have to write. So ultimately, the syndrome will have 3 bits, right? Because if we consider that K was 3 bits or my message had 3 bits. So syndrome would have 3 bits, S1, S2, and S3. S1, if you do the multiplication, you'll see that S1 is a summation of 3 of these received vector bits. For example, R1, R4, R1, R4, R6, and then S2 will be some again summation of 3 bits of this received vector. S3 will also be the summation of 3 bits of this received vector. So if you can deduce this, you can easily implement it using your logic gates. So S1 will basically be the modulo to addition of R1, R4, R6. You can actually find them out by yourself. If you know your H will be what? It will be I n minus k most probably and P. Okay, so it's written in your lab sheet and you can also refer to your book. So if you do the multiplication, you'll see that your S1, S2, S3 can be written down in as these bits of your received vector. So by using this equations, you can actually build your logic gates, or you can place your logic gates. So using XOR gates, you can find out your S1, S2, and S3. After that, what you have to do is so the syndrome testing is done. That is, you have found out the syndrome. What's the next step? The next step is to compare it with a lookup table of your error patterns. So to compare it with the lookup table, you need to produce that is, here all your syndromes will be 1, right? So you have to produce different combinations of your syndromes to produce different error patterns, and that is being done here using your AND gates. And then once you have produced your error patterns, you then add your received vectors with that. You add your received vectors with that to find out your code words. Okay, so that's what has been done in this decoder. So you can go through it by yourself. If you have any problem, we can have a discussion class regarding it. Then this part is, you have already done a lot of, you have already built a lot of, you have already done some Simulink models in your previous labs. So this part should be pretty easy to you. Your job will be to build this. Building this is very easy. This is basically your coder and decoder. So your job will be to build it and analyze the results from your scope, okay? So you can do it as your home task. And the block parameters are also given, so it won't be difficult for you. Do it. Okay. Now let us come to the coding part. So we have learned about encoding and decoding, right? So whatever we have learned we have learned about how things flow in encoder and decoders. The things that we have learned, will now be translated into codes. So the codes are very easy. Let us just go through them quickly. Look at the encoding part. First of all, they have built a generator matrix, and the generator matrix, since it is a systematic linear block code that we'll be working with, the generator matrix consists of a parity part and an identity matrix. So I actually is your identity matrix. So I built-in function actually helps you to get to your identity matrix, and the number inside the bracket actually is the dimension of your identity matrix. So the dimension of your identity matrix also tells you how many bits will be there in your messages. So since here it's 3, we can say that our K is 3 for this case. So once you have built your generator matrix, the next thing will be your next job will be to extract the rows or vectors of your generator matrix. So that is what's being done here. You're extracting the first row and storing it as V1. You're extracting the second row and storing it as V2. And you're extracting the third row and storing it as V3. The next step will be what? The next step will be to linearly combine them with your message bits, right? That is, you combine your V1 with M1, then you combine your M2 with V2, you combine your M3 with V3. That's what has been done here. By combining, we mean that we want to AND them, okay? And then what do we have to do? To reach to the code word, we have to modulo add them, right? Or XOR them. So that's what done. First of all, these two are XORed by bit XOR, and then the result of that is XORed with M3 into V3, okay? So ultimately, you can reach to your code word. So that's what has been done in this encoding part. It's very easy to understand, but this is not the only way in which you can actually encode. You can have, if you have understood the theory, if you understand how encoding is done, then you can build your own codes, okay? So this is just a demo for you. Then let us go for decoding. What do we have to do for the decoding part? We need a parity matrix, right? We need a parity check matrix. And we need to do syndrome testing. So we need a received vector. With that, we have to multiply the transpose of our parity check matrix. And the result of the syndrome will then need to be compared with the lookup table, or will then need to be used with the help of a lookup table to find out my error pattern. After I have found out my error pattern, then I have to add this error pattern to my received vector to get to my original code word. So here I have built my transpose. Here I have built my parity check matrix. Here I have found out the transpose of my parity check matrix. Then I'm using these for loops to linearly combine my received vector, received code word, and the transpose of my parity check matrix. So you should go through this properly. This is very easy to understand, but you have worked with for loops before. So first of all, we will start a loop and iterate it 3 times. Why 3 times? Because your syndrome will consist of 3 bits, right? Because because our case 3, our linear block code's case 3, and our linear combination will look like this, right? R1, R2, R3, R4, R5, R6. And then you have your transpose of your parity check matrix. So for S1, your S1 will be basically what? R1 into this, R2 into the second element of your first column, R3 into the third element of your first column, and so on, right? So first of all, the first for loop will help you to the first for loop will help you to iterate from one element to the next element, right? That's why it is the boundaries for it are 1 to 3, right? And the second for loop will actually help you to move on, or will help you to do iterations for the rest of the bits in your code word. okay, for the first column, okay? And then for I is equal to 2, the second column will be dealt with. For I equals to 3, the third column will be dealt with. So 1 is to 3. This for loop is for each of the columns in your parity check matrix. And each of these columns will ultimately result in, or multiplication with each of these columns or with the first element of each of these columns with the first element of your received vector will actually give you your S1, S2, will actually initiate or start the calculation for your S1, S2, and S3 respectively, right? And this for loop will continue the calculation for the rest of the bits in your code word for each of these columns, right? So that's what the second column, the second for loop is for. So after the implementation of these two for loops, you will be left with a syndrome, and then you have to compare, or you have to find out the corresponding error pattern for these syndromes from the lookup table. So the lookup table will be given to you. The parity matrix will also be given to you. And from the lookup table, you can use if-else condition to find out the error pattern, to find out the code word. That is, by using the lookup table, you can build your if-else conditions. So if your syndrome is 0, then your error pattern has to be 0. And if your error pattern is 0, then your received code words is basically your actual code word. So instead of XORing it, you just can write that y is equal to your x here, right? If your syndrome is 101, then your error pattern will be this according to the lookup table. So if you have found out your error pattern, your next step will be to add the error pattern with your received vector, right? Here our received vector is x and our code word is y. So you just have to XOR your x with your e or error, right? That's what you'll do using these if-else conditions. And that's it. Okay, so in your encoding, you need a generator matrix, and then you have to extract the contents or the vectors or rows of your generator matrix, and then linearly combine it with your message bits. For your decoding, you have to find out your, or you have to extract your parity check matrix from your generator matrix, and then use that for syndrome testing, and then you can use the lookup table to deduce the error patterns and then add those error patterns with your received code word to find out your original code word. That's it. So that's what this lab is about. For the quiz, we will be asking questions from the theory primarily because this theory is very important. And you should also go through the codes. The codes are pretty easy to understand. And once you have gone through this lecture, I'll ask you to go through the book as well. The book that we had, yeah. You can go through this book, Digital Communications by Bernard Sklar. So in this book, chapter 6, article 6.4 will give you a good idea about linear block coding. So you can go through it. It's very easy to understand. And then if you have any problem, then we can discuss it you can ask for a discussion class and we can discuss it later. So for now, let me just end this lecture, and I will try to upload a lecture video on this linear block coding part, but it's pretty easy actually. You can just try it yourself at home and analyze the results. So your report should consist of the analysis of the results that you get from your scope, and this in, and yeah, that's it. And at home you can find out some code words, or you can find out some 3 bits and then convert it to a code word, and then introduce some errors in that and then go for decoding. Okay, so you can practice these things at your home on your own. So let me end the class here. Let me end the lecture here today. If you have any questions, you can write them in the comments. And if you want a discussion class, then please let me know. Thank you.